In this video, we're going to be looking at how to draw a Lewis dot diagram, assign formal charges, and also draw the resonance structures of some molecules. So let's get into it. Let's look at how to draw the Lewis dot structure of the following compounds, beginning with dichloromethane. Dichloromethane has carbon, hydrogen, and chlorine. So in order to draw the Lewis dot structure, there are certain rules that need to be followed. The first rule is that you always have to identify a central atom. So the central atom is the most electropositive. So most electropositive. And to be able to identify the most electropositive, usually is the one that has the most bonding. So looking at carbon, hydrogen, and chlorine, carbon will obviously be the central atom. The rule number 2 is that each one of these atoms will be connected to the central atom by single bonds first. And then when there's a need for it, you can double the bonds. The rule number 3 is that you calculate all the valence electrons in the bonds. So to do that, you have to obtain the valence electrons for each one of the atoms. And if there's more than one atom, you multiply it by the number of atoms and add all of them together. The next rule is that you would then distribute these valence electrons around the different atoms. And some exceptions exist. Hydrogen can take only 2 electrons. Certain atoms would defy the octet rule because when you're distributing these valence electrons, the whole idea is to make sure that every atom satisfies either the octet rule for most atoms or the doublet rule for hydrogen. Now, there are certain atoms that defy the octet rule, and this includes sulfur, phosphorus, and even chlorine. So these atoms tend to have an expanded octet exception, meaning that they can have more than 8 valence electrons in the molecule. So let's solve that of dichloromethane, and all these rules will make some sense. So rule number 1, identify the central atom, carbon. Attach each one of the atoms in this molecule to the central atom. So we have 4 of those, 2 hydrogens and 2 chloride atoms. Identify all the valence electrons for each of the atoms. Hydrogen has 1, and there are 2 of those, so a total of 2 valence electrons. Carbon has 4 valence electrons, and there's only 1 of those, so that gives us 4 valence electrons. Chlorine has 7 valence electrons, and there are 2 of those, that gives us 14 valence electrons. So if you add all of this together, that gives us 20 valence electrons. The next thing to do is to go back to the structure and distribute these 20 electrons amongst all the atoms. Each bond uses 2 valence electrons. So what that leaves us with is 12 electrons because 8 will be taken out of this 20, and therefore we'll be having 12 valence electrons. So we have 12 valence electrons to distribute amongst the atoms. The first thing you look at is which atom has an octet. Of course, we can see clearly carbon has an octet satisfied because it has 8 electrons in its outer shell. Another thing you should pay attention is that these atoms that are shared in a bond can be counted for either atoms. So it can be counted for carbon, and it can also be counted for chlorine. So as you can see, at this point, chlorine only has 2 electrons, and it needs about 8 of those. So what that means is that we can go ahead and give 6 electrons to each one of these chlorines. But when you're doing it, you put it in as a pair of dots, and each dot is an electron. So with that said, you now see that if you watch closely, the chlorine now has 8 electrons in its shell, and it has an octet satisfaction, and the same thing applies to this chlorine. So overall, this will be the Lewis dot structure of dichloromethane. Next, we're going to talk about the dot structure for boron. Boron is made up of boron and hydrogen. Boron has 5 electrons, and its electronic configuration is 1s2, 2s2, and 2p1. That tells us the valence electrons for boron, or boron I should say, is 3. That of hydrogen, we know is 1. And since we have 3 of those, that will give us 3 valence electrons and 3 valence electrons for boron. If you add this together, you will have 6 valence electrons. So now that we know that boron has 6 valence electrons, we're going to distribute these 6 valence electrons amongst the atoms. But first, we need to identify the central atom. And this is pretty easy because boron is the most electropositive. Hydrogen will be attached to boron. And now we're going to distribute these electrons on these atoms. So we remember that each bond has 2 valence electrons. So eventually, we have 6 valence electrons used to form all the bonds. So there's no more electrons left. But guess what? Boron is still not obtained an octet. And it's fine with that. Because boron is one of those exceptions to the rule. It is fine without having an octet number of valence electrons. And therefore, it is very reactive because, of course, it doesn't have an octet and is always looking for electrons and can easily react. And also, the p orbitals can engage in reactions. And that is the dot structure for boron. Now, let's take a look at sulfur dioxide. Sulfur dioxide has sulfur and oxygen. Of course, sulfur is going to be the most electropositive because oxygen and sulfur are in the same group. They're in the group 6. So they have 6 valence electrons each. Now, sulfur is going to be the central atom connected to oxygen. So now let's calculate how many valence electrons each one of these have. So sulfur has 6 valence electrons and is only one of those. So that gives us 6 valence electrons. Oxygen has 6 and is 2 of those, so that gives us 12 valence electrons. So if you add it together, you have 18 valence electrons. The interesting thing is that already 4 of those electrons have already been used. We have 4 taken out of 18, that leaves us with 14 valence electrons. So let's just distribute these 14 valence electrons on these oxygen. So usually you put the lone pairs of electrons on the atoms. I'll put about 6 on each of these oxygen because oxygen loves a lot of electrons, and put 2 on the sulfur. Now, how many do we have? We have 14, so we are good. If you did look at the octet, oxygen has a complete octet here and it has a complete octet here. But you don't have sulfur having this octet. It actually has 6 electrons because each one of these bonds has 2 electrons. So now we can easily use 2 of these lone pairs of electrons from oxygen to form a double bond so that sulfur can have an octet. So now we have sulfur that has a double bond to this oxygen on your left and another oxygen on your right. These lone pairs will be drawn far apart because now one of it is used to form this bond. And in this particular oxygen, you still have 3 lone pairs of electrons drawn far apart from each other. And of course, the sulfur has 2 lone pairs of electrons. At this point, every atom in this structure has satisfied the octet. 8 for sulfur, 8 for both oxygens, and we can actually leave it as this. But the interesting thing is that very soon we're going to look at formal charges anyway, but sulfur in this form will have a positive formal charge, and oxygen in this form always has a negative formal charge. So to avoid that, a pair of this lone pair will be used to form a double bond here to kind of remove all these charges that we're going to talk about later. So that will give us sulfur dioxide that has double bond to an oxygen and only 2 lone pairs here, and then another double bond to this oxygen with only 2 lone pairs. And of course, there will be lone pairs of electrons on that particular sulfur. So with that, this will be the dot diagram for sulfur. If you look at sulfur, it has 10 electrons in its valence shell. So that is what we meant by sulfur defies the octet rule in order to be stable. So now let's look at the nitrous ion and its dot structure. The nitrous ion has nitrogen and oxygen. Between these two, nitrogen is the more electropositive, so nitrogen will be the central atom. So with the nitrogen being the central atom, all the other atoms will be connected to it, and we have 3 oxygen atoms that will be singly bonded to nitrogen. The next thing we do is to add all the valence electrons in the structure. We know that nitrogen has 5 valence electrons. Oxygen has 6. And because we have 3 of those, that will give us 18 valence electrons. And we will only have 5 coming from nitrogen. And because this species has a negative charge, there's 1 extra electron. So if you add all of that, that gives us 24 valence electrons. With 24 valence electrons, we already know 6 of those have been used in forming these bonds. So if you subtract 6 from this, that leaves us with 18 valence electrons to distribute. So with 18 electrons to distribute, let's see how that goes with the oxygens and the nitrogen. So first of all, you give lone pairs to each one of these atoms. At this point, we have expended 8 lone pairs, so that leaves us with 10. We will go around again and give each one of these oxygen another pair. And if we did that, we'll be left with 2 lone pairs or 4 electrons. With 4 electrons, it will be wise to give 2 to this oxygen and 2 to that oxygen. This way, these 2 oxygen atoms will have an octet satisfaction. So with that out of the way, let's see how nitrous ion looks like in terms of Lewis-Dog structures. So the central atom will be nitrogen connected to 3 oxygen atoms. Nitrogen has valence electron of 5. Oxygen has valence electron of 6. If you do the math, there's only 1 of nitrogen that gives us 5 valence electrons. And there are about 3 of the oxygens in the structure, so that gives us 18 valence electrons. Remember, this is a charged molecule, so therefore we have 1 valence electron hanging around as well. So that gives us 24 valence electrons. Remember that each of these bonds contains 2 electrons. So already we've spent 6 electrons. That leaves us with 18 valence electrons. We are now going to distribute these 18 valence electrons around these atoms. So let's begin by putting each one of the atoms with 2 valence electrons. So we do that, and that spends 8 electrons, leaving us with 10. We can now do another distribution, making sure that every atom has an octet. So we just spent, that's 4, 4, 4, 2, so 14. We still have 4 left. We can give 2 to this one to complete its octet, and 2 to this one to complete its octet. Now, you look at nitrogen, octet is complete, but this particular oxygen does not have a full octet. So to help it out, nitrogen can share its lone pair of electrons with this, and it will give us an octet electronic configuration. So that will leave us with nitrogen that is double bonded to this particular oxygen, and that oxygen will have 2 lone pairs of electrons, and is connected to 2 other oxygen atoms that have 3 pairs of lone pairs on these oxygen. Looking at this structure, you realize that every atom has a complete octet. So nitrogen has 1, 2, 3, 4 bonds, and each one of them has 2, so that will be 8. Oxygen has that too. So all of them have complete octet in this case, and therefore you can put it in a bracket and put a minus sign on there. But one thing I should say is that if you want to really look at it, the atoms in the structure, nitrogen will have a plus charge. These 2 oxygen molecules will have negative charge each. And when you do the sum of charges, it will end up with -1 net charge. Now that leads us to the next topic of assigning formal charges. In order to assign formal charges for any compound, you have to draw the Lewis structure of that compound. So let's do that by illustrating it with an example. Let's go back to nitrous ion. We identify that nitrous ion has a central nitrogen atom that is double bonded to an oxygen and single bonded to 2 oxygen atoms. We also saw that the lone pairs on the double bonded oxygen are 2 and 3 for the single bonded oxygen atoms. Now let's try and assign formal charges for each one of these atoms. To do that, formal charge is given by the formula valence electron of that particular atom minus the number of non-bonding electrons plus half of the number of bonding electrons. So let's take an example and see how we're going to assign the formal charge on this particular nitrogen. So formal charge for the nitrogen would therefore be 5, which is the valency for nitrogen, the valence electron for nitrogen, into bracket, number of non-bonding, and as you can see, nitrogen has no non-bonding electrons. All the electrons are involved in a bond, so that will be 0, plus half of the number of electrons in the bonding. So if you see, every bond has 2 electrons, so it gives us 8 electrons overall that are involved in bonding. So that will be 8 right here. If you did the math, that will give us 5 minus 4. And this will give us a plus 1. This nitrogen will have a formal charge of plus 1. Next, let's look at one of the oxygens that are connected to the nitrogen. So to calculate the formal charge on this oxygen, so we have oxygen number 1, let's label them 2 and 3. Both 2 and 3 are the same. So in order to calculate the formal charge on 3 or 2, we're going to look at the valence electrons for oxygen, which is 6, minus the number of non-bonding electrons. In this case, you have 6 of those, plus half of number of bonding electrons. So you only have 2. So if you did the math, it will lead us to 6 minus 6 plus 1. And overall, you're going to get 1 minus 1. So the formal charge on this oxygen will be minus 1. And it will be the same thing for this particular oxygen as well. Let's try and see oxygen number 1. So formal charge for oxygen number 1 will also be 6 minus number of non-bonding, which is 4, plus half of number of bonding, which is also 4. This will leave us with 6 minus 4 plus 2. And this will give us 0. So there's no formal charge, the formal charge on this oxygen is 0. If you did a net charge on this particular species, you realize that the negative charge on one of these oxygen can neutralize the positive charge on that nitrogen. And overall, this is going to have a net charge of minus 1. Example 2. Let's look at how we're going to draw or assign a formal charge for the carbon in this structure. So formal charge of this carbon will be giving us the valence electron of this carbon, which is 4, minus the number of non-bonding electrons, which is 0, plus half of number of bonding electrons. So as we already know, every bond has 2 electrons. So that gives us 6 electrons. So that will be 6 electrons. So if you did the math, this would be 4 minus 0 plus 3. So that gives us plus 1. So this carbon is going to have a formal charge of plus 1, and it's also called the carbocation. And this is a very interesting species that you encounter in organic chemistry. Example number 3 looks at a carbon with a lone pair of electrons. So to calculate the formal charge of this particular carbon, we're going to look at the valency of the carbon, which is 4, subtract it from number of non-bonding, which in this case is going to be 2, because you have 2 lone pairs of electrons, plus half of number of bonding electrons, and we have 6 bonding electrons. So if you did the math, the formal charge will come to 4 minus 2 plus 3. If you did that, you get 4 minus 5, giving us minus 1. So the formal charge on this is minus 1. And this is also called a carbanion, and a lot of reactions will happen via the carbanion in organic chemistry reactions. When you look at aluminum tetrahydride, you can assign the formal charge by drawing the Lewis structure of aluminum tetrahydride. So that will give us aluminum connected. Aluminum will be the most electropositive, connected to 4 hydrogens. And each bond, as we mentioned, is made up of 2 electrons. So let's try and calculate the formal charge on the aluminum. So formal charge on aluminum will be the valence electron of aluminum, which is 3, because aluminum belongs to the group that have 3 valences of electrons. So it has 3 minus the number of non-bonding was 0 plus half of bonding electrons, and in this case we have 8. So if you went on, it would be 3 minus 4, and you get a minus 1 as the net formal charge on this aluminum. So that will be minus 1. So aluminum tetrahydride will have a charge of minus 1. Now let's look at resonance structures. In organic chemistry, resonance structures are just representation of the same molecule, just that lone pairs of electrons, pi bonds, and charges move around the atom. Let's illustrate this with an example. Let's begin with acetate ion. The acetate ion has 2 oxygen atoms that have one of them has a formal charge and the other one is neutral with 2 lone pairs of electrons. In order to write the resonance structures, you usually use double arrows to connect the different structures. So in order to do that, you will move charges onto sp2 hybridized atoms. And as you can see, this carbon is sp2 hybridized because it's connected to 3 groups, oxygen, 2 oxygens, and a carbon. That makes it sp2. This oxygen is also sp2 hybridized and can take some electrons. So you will move these 2 lone pairs of electrons that onto this bond, onto this single bond, and now carbon will have 5 bonds. And in order to adapt to that, one of these pi bonds will have to pop open and will be put on the oxygen. So as a rule, you always move electrons or pi bonds onto atoms, and you move negative charges or lone pairs onto single bonds that are sp2 hybridized. So that will leave us with this oxygen that now has 3 lone pairs of electrons and it's negatively charged. That's a formal charge, and then a double bond between these 2 carbons with only 2 lone pairs of electrons at this point. Now these 2 structures is what we call the resonance contributors. So these will be called resonance contributors. And as a rule, usually write and put both contributors in a parenthesis connected by double arrows. You can actually write a hybrid for all of them. And a hybrid for the structure usually shows you how the electron is moving within the molecule. So we can say that the hybrid for acetate will have the oxygens, and then you illustrate it with dotted lines to show how the negative charge is distributed or delocalized amongst these 2 oxygens. So this will be called the resonance hybrid. And it only shows the delocalization of electrons. So now let's look at example number 2, where we're going to draw the resonance structure of aniline. Aniline is a benzene structure with a minor group. So in order to draw resonance structures, there are certain common rules we already reviewed. First of all, you need to find out if there are any lone pairs of electrons. And you should also have pi bonds. And most of all, you should have sp2 hybridized atoms. looking at this structure, almost all the atoms in the benzene ring are sp2 hybridized. So that makes it easy to push electrons. So let's begin our electron pushing with a lone pair of electrons. So the first thing we will do is to move these electrons onto this sp2 hybridized bond. And because now carbon will have 5 bonds, this double bond, pi bond right here will shift onto this carbon. Now remember, pi bonds always move onto atoms, and lone pairs of electrons will move onto bonds. So with that in mind, we can now draw the next resonance structure with a double arrow and keep it following the electrons. So since these lone pairs were moved onto this bond, you will now have a double bond with a nitrogen. And since nitrogen has lost its lone pair, it will have a formal charge of +1. Now this carbon will have a negative charge with 2 lone pairs of electrons, and all the other pi bonds will stay as it is. The net charge on this resonance contributor should be the same as the net charge of the original structure. So if you add plus and minus, that gives us 0, which is the net charge of aniline as we started with. Now let's move on to the next resonance structure. At this point, we can move these electron pairs around. So to do that, this electron will be moved onto the bond, and whenever that happens, the pi electron will move onto the next carbon because these carbons are sp2 hybridized. So that gives us the next resonance structure with this nitrogen plus on there. Now we have a double bond right here. However, there's a negative charge on this carbon, and then the pi electron on this side stays as it is. So we're going to go on with the next atom, meaning we have a lone pair here which will also be moved. So let's pick a different color, and that lone pair will be moved onto the next bond, and again this pi electron will move onto this carbon. So that leaves us with another resonance contributor where you have a double bond here, nitrogen plus, and now you have a double bond established, and the negative charge moves on here with a lone pair. And then the last structure will be to move this lone pair here, and then you have the bond moving on to the electron sink. So to be consistent, let's take a different color. So this lone pair of electrons will move on to this bond, and that pi bond will pop and go into the electron sink of the positive charge. So you end up with something that looks like this. So you will have your double bonds this way, and your nitrogen lone pairs established like that. So you will have 1, 2, 3, 4, 5 contributors. So you have 5 resonance contributors for aniline, making it very stable in that sense. So the last thing you do is you put all of them in a bracket. In example 3, we're going to draw the resonance structure of the benzylic carbocation, which is one of the most stable carbocations you encounter in organic chemistry. To begin with, let's look at all the atoms and their hybridization states. It's very interesting to note that all the carbons in the structure are sp2 hybridized. So that makes it easy to push electrons onto. We will begin our electron pushing by looking at the calculate structure of the benzylic carbocation. So calculate structure means you push the electrons into alternative single bonds in the benzene, and that will give us our first resonance contributor. So draw the benzene ring, but this time we have the pi bonds alternating to give us this carbocation. Now that we have the carbocation, we can begin to push the electrons from the benzene pi bond system onto the sp2 bond. So I'll begin by looking at moving this electron onto that bond. When you do that, it will leave us with a double bond formed between this and the carbon, but then the plus sign will be gone because now you have a fully octet. But then the carbon from which we got this double bond from will have a positive charge because we took electrons from this carbon. The other pi bonds will stay the same. Next, we're going to keep moving the pi bonds towards the positive charges. And if you did that, it will bring a positive charge to this carbon right here. So let's write the resonance structure that will result from that. So you have a double bond here. Now you have a double bond formed with a plus charge on this carbon, and of course the pi bond right there. The next thing we're going to do is to move the last pi bond, in this case this particular one right here. If you did that, it will put a positive charge on this carbon right there. So let's draw that one to complete the resonance structures for benzylic carbocation. So that will give us a double bond right here, and there's the existing one, and then you have the double bond connecting the methylene group, and this will give us a positive charge right there. So you can see we have 1, 2, 3, 4, 5 benzylic resonance structures, and because of that number of resonance structures you can write for the benzylic carbocation, it makes it very stable. In example 4, we're going to look at a resonance structure for nitrobenzene. When nitrobenzene is written as this, you might have to expand this so that you see the electrons in the Lewis structure form. So to do that, we're going to expand this and put a Kekuले structure for the benzene, and then the nitro will have oxygen attached to the nitrogen, and this is how it looks like. So nitrogen can form 3 bonds, and the last bond that is connected to the oxygen is some sort of a dative covalent bond. So let's take a look, and of course we will have to draw our Lewis structures. The lone pair of electrons for the nitrogen is kind of shared with this oxygen. So to begin with, we're going to do the Kekuले structure like we did before, do the alternative, push the pi bonds into the single bonds, and if you did that, you will get a Kekule structure as the first resonance contributor. So let's draw the benzene, nitrobenzene. So this time you have the bonds alternating in a different direction. So the nitrogen will stay the same with the oxygen. Next, we're going to start pushing these electrons onto the sp2 hybridization. So let's try this with trying to push the electrons from the benzene ring onto this nitrogen. And if you did that, it will be having nitrogen will be having excess number of bonding, and therefore this pi bond right here will pop open. So if that happens, you're going to have a positive charge on this carbon right here and a negative charge on this oxygen. So let's see how that will look like. So we will draw the resonance structure where we keep the other pi electrons the same, but then remember there's going to be a positive charge on this carbon because we're taking the electrons from that carbon and using it to form this double bond right here with this nitrogen, and of course the oxygen will have a negative charge because you put the pi bond onto the oxygen, and there's this dative bonding with the oxygen. So you go on to the next one, meaning you can move this positive charge around the carbons in the benzene ring. So if you did that, you're going to move this right here, and of course the positive charge will be on this carbon. So let's see how that one will look like as well. You have your benzene, double bonded to nitrogen, single bonded to that oxygen with a negative charge, and of course this will have 3 lone pairs of electrons that is connected to this oxygen. The same thing applies here, and we will have a positive charge right here, the new form bond, and the existing pi bond right there. So we go on to the next resonance structure, And what you're going to do is to move this lone pair of electrons, or move the pi bond to this positive charge. And if you did that, you're going to have a positive charge on this particular carbon. So let's see how that looks like. So we have our nitrogen double bonded, single bonded to this oxygen, and you have that dative bonding to that oxygen. But now we have a positive charge on this carbon, a new formed bond, and another bond right here. So we have about 1, 2, 3, 4, 5 different resonance structures you can write for nitrobenzene, making it very, very stable as well. Now that we know how to draw resonance structures, let's take a minute and see how we can select the best contributor to the resonant hybrid structure. To do that, there are certain rules to be followed. So rule number 1, you always pick the resonance structure that have a full octet over the one that doesn't. So full octet is preferred. Rule number 2, you always select the resonance structure that has the most covalent bonds. So most covalent bonds. Rule 3, you always select the resonance structures that have less charges, so less formal charges, and preferably if it doesn't have any, preferably if it is 0. So those ones will be major contributors. Now rule number 4, when it comes to negative charges, you always try and give the negative charge to the more electronegative atom or element. So more electronegative will be preferable. And also, you always give it to the larger size. So if there are 2 elements, the larger size element should accommodate the electron. Right. Rule number 5 is that we will prefer to have an aromatic system. So an aromatic contributor will be better off than a non-aromatic. So we will illustrate this with more examples. In these examples, we're going to draw and identify the major and minor resonance contributors. Number 1 is acetone. You have 2 sp2 hybridized groups. So you have this oxygen and that carbon. So we can move some electrons. So if you move this pi bond onto this oxygen, which already has 2 lone pairs of electrons, you're going to get the first contributor for this structure. So this contributor will have oxygen that has 3 lone pairs of electrons and has a formal charge. And then the carbon sitting in the middle will have a positive charge because those electrons were taken away from it. Now, this will be the only resonance structures that will be written. But guess what? Between these two, so we have A and B, which one is going to be a major contributor? Going back to the rules, we expect that A will be the major contributor because 1, it has no formal charge, and 2, it has all full octets, so it has a complete octet for all the atoms. Whereas in B, this atom right here is incomplete octet. So that makes it least stable contributor. For example 2, we're just going to move this pi electrons into this oxygen, and that will provide us with the resonance structure. So let's see what you're going to get. You're going to get a single bonded oxygen with a hydrogen, and you're going to have 2 lone pairs of electrons, and the carbon is going to have the positive charge. So as you can see, in this case, you have an octet. You have a lone pair on this oxygen, so there's an octet satisfaction, but there's no octet satisfaction here. So we would prefer this as a major contributor and that as a minor contributor. Let's look at number 3. Number 3 will have this negative charge on the carbon for this species, which can be moved onto this sp2 bond, and that will pop this pi bond open. So that will give us an oxygen and a double bond carbon, and the negative charge will be on this oxygen. So in this case, we would prefer to have the negative charge on this oxygen for this contributor, as opposed to having a negative charge on this carbon. So this will be a minor contributor because it's not stable, and this will be a major contributor.